Hello, everyone. Thank you for coming for our webinar. I'm Veronika Hegrova, and I'm Application Manager. And today, I'd like to show you what we measured from powders and particles and 2D materials. And I'd like to show you our key benefits of such a characterization. So let me share my screen. In the meantime, if you have any question, uh, please write it on the Q&A session. My colleague will answer it right away during the presentation. So here it is. So you should now see the screen. And so what we're going to talk about. We'll start with a brief introduction of AFM-in-SEM technology. And then further, we have a look at the challenges and needs for future technologies and why we need to measure powders, particles, and low-dimensional materials in general. And so afterwards, we get into the application examples and use cases. And at the end, we summarize what we talked about. So let's start with the AFM in SEM, how it actually looks like. So if you have a look here, we have the light scope, a unique atomic force microscope, which fits into almost any SEM chamber. And so we have light scope sitting on the stage. And over here, you see the SEM chamber and the objective over here. So there are just two cables which need to be connected, and we install this procedure each time before the measurement, so we don't occupy the chamber when not needed. And so I would like to start with the motivation, why we actually started with AFM in SEM at the beginning. So the reason is quite simple, as both of these technologies are quite widely used in nanoscale measurements of surfaces. Because each of these technologies use different principles, that's why it's great to have it together, and it's complementary. So in case of AFM, we measure with a probe, physical probe. So we basically almost touch the surface, and we are able to acquire precise 3D topography with mechanical properties, electrical properties, magnetic properties. Basically depends only on the probe which we use. On the other hand, SEM uses a focused beam of electrons, so we can have very fast 2D imaging, wide field range. We can modify the surface or use the EDS or other systems to have the elemental composition of the surface, crystallographical structures. And all of them we can then combine into a CPAM image. And so if I should point some of the benefits, I would definitely say it's in situ sample characterization, because we have everything under in situ conditions. So there is no need of transferring the sample, no need of changing the actual conditions. So we are there. And we are able to measure several different modes from different instruments together and correlate them and see the changes, what's happening, and then precise localization to the region of interest, which can be quite tricky when we have different contrasts and we don't know what we are seeing, or it takes time. So what we are focusing on is to provide information about the samples which are otherwise unable to acquire, or they are extremely complicated or time-consuming. And so what modalities we have and what we can combine. I would divide it into 4 groups, from mechanical properties, of course, topography, dissipation, phase imaging, to have or quantitatively nanoindentation for mechanical properties, elastic or plastic deformation. From electrical properties, conductivity mapping or local surface potential mapping, or electrostatic force microscopy. We can measure magnetic domain imaging, piezoelectric domains, or we can measure all of these techniques in a spectroscopy mode. So either biasing can be visible, force distance spectroscopy, or time spectroscopy. And all of these techniques we also can correlate together and explore the differences and maybe understand the fundamental properties of our surface. I would divide our application areas into 4 groups. Material science, such as low-dimensional materials, steels, metals, ceramics, batteries, or in nanostructures, the advantage of having focused ion beam or gas injection system is quite nice if we don't know the parameters which should be set. So we can go back and forth to fibbing and doing the probe analysis. Semiconductors, they're definitely failure analysis or current leakages in integrated circuits. And in life sciences, measurement of cells or proteins or pharmaceutic industry, I would put as well there. So, but today we'd like to focus more on powders and particles and 2D materials. So if I should introduce it a bit, why? Because microscopic properties directly influence the macroscopic functionality of the device. So if we have a different sizes and shapes of a compound, which we study on a micro scale, it will definitely change the properties of the whole device. So that's why the surface properties can be critical for the macroscopical functionality afterwards. And so if we go into these powders, particles, and 2D materials, where it changes, what is the future? Definitely the development needs to be, or influences, or measurements in drug delivery, in pharmaceutics, additive manufacturing, semiconductor devices, battery and energy storage, or catalysis in chemical industry. And so why we study it? Because afterwards it enables us to have lighter or stronger materials, or enhance the performance and efficiency of the devices which we already have. Another one where many universities and many research institutions are searching for is how to recycle well or more efficiently. And so AFM-in-SEM technology represents a unique solution for determination of surface roughness of powders and particles, which is key in influencing the production processes and reproducibility. And complex sample characterization is crucial for the 2D materials, which still reproducibility is kind of an issue, but it has perfect properties, so it would be sad if we can't use it on the maximum. And so let's get into the powders and particles. Here is a recording how it can look like. So we have a powder particle over here, and then the tip tapping into the surface, so we can get the, for instance, topography, roughness of the material directly. And so why we study powders and particles? Because the interactions between one powder particle and the other is very important in understanding the fundamental principles for industrial processes in pharma, in ceramics, paints or coatings, etc. And so these interactions are different according to the surface roughness, which we have as well. So these interactions will change how it's adhesive or how other treatments are binding onto it. Not only the roughness, but as well other properties such as mechanical or magnetic can help in understanding the principles of devices. And so if we go into surface roughness measurement, I'd like to show you an optimized solution, how we measure the surface roughness. As on two cases, we will see a use case of in pharmaceutics and in ceramic powder. So before that, what is the measurement workflow? So first of all, we need to find the particle and navigate the tip onto the particle. Afterwards, we can measure the surface and calculate the roughness. And so if we have a look how it looks like, so we can see from top that we are finding the structure, then navigate the tip on top of it, which is quite many times quite difficult if we don't have SEM. So SEM really helps that we can see the very end of the tip. And then we approach to the particle. So this is under the tilt. It's not necessary, but it's nicely visible that it safely goes using auto approach, so we don't have to take care of it. Now we also have a built-in software to determine the roughness of the sample surface. So of course, without background correction, it's impossible to get the roughness. So we have different background corrections which you can use, which fits the best to your surface. Then you can select the area using different rectangle, circular, or polygon, and select the area. And afterwards, we can calculate different parameters of the roughness and export the data in the text file. So it's quite easy to get the data out afterwards. And so regarding the data processing, it can be the fit can be polynomial or spherical, and we can see it over here. And we choose the squares. Over here are visible the roughnesses, and we export it. So already we see it in the software that it's quite easy. And let's get to the first use case in pharmaceutics. So surface roughness in powder particles is quite crucial in order to understand how the active pharmaceutic ingredient, or API shortly, attaches to the carrier. So we can see it over here. We have a carrier powder particle. Then we have the treatment, which we have to put onto it. And then the carrier is full or depends on the treatment. The treatment attaches to the carrier. And so the ideal case is that we will have the carrier only in the pores. That's why the powder particles roughness is so crucial. But what can happen that the active ingredient gets out of the pores and it recrystallizes, and then it has different properties and doesn't work well as it should. So that's why we need to understand the roughness of the particle at the beginning, but as well the roughness after the treatment when the active ingredient is attached. So we measured different powder particles, and we watched how the active ingredient attaches the surface. And we could measure it directly because we have the AFM inside SEM. And so let's have a look at the powder particles. So we can see SEM image and TEM image of the mesoporous silica particles. They can create clusters or they can be single particles. Depends on how much of the powder is on the sample. And so the key aspects and interest which we had was what is the particle texture and what is the difference in the surface roughness of particles with API and without the active ingredient. So we can compare it afterwards. And so I have one more time, and this time the actual sample which we measured. So we chose the particle, we navigated to the particle, we approached and measured the topography to obtain the surface roughness, and then we calculated it. So there is a complete workflow for the quick analysis. And if we have a look at silica particle without API, we can see the SEM and AFM of the sample surface just in the middle, somewhere here. And then we measured the silica particle with active ingredient. We had several different percentage of the treatment. I have one of them over here, and we can see that the treatment is partially visible in the SEM, but not perfectly, and definitely we don't know where the active ingredient is. The topography in this case helps us a lot in seeing at least the active ingredient which is on top. And so we can see that over here are the active ingredient covers the particle surface. And what we didn't know was whether it recrystallized and the treatment got only here or it got everywhere. So the roughness comparison helps us in this case. So if we have a look, we can choose which part we want to take in account if there is an impurity or something which doesn't make sense to count. And we can see that the surface roughness is smaller due to recrystallization of the treatment. So this is the API, but it's higher everywhere else. What it means that we are in a case where all the pores were filled, and then the active ingredient recrystallized above it. So it seems that the API is in the pores, but as well as on top of the carrier. And so if I should sum it up, AFM-in-SEM is a unique tool for direct analysis of the surface texture and roughness determination. What we found out is that the active ingredient is bound in the pores, but depends on the amount of the active ingredient. It can be either only in the pores or covering the whole carrier top. And that is the reason why the surface roughness with the active ingredient particle is higher, as the active ingredient recrystallized and created the clusters on top of it. So this is a use case where I want to show you how effectively it is possible to measure the surface roughness of powder particles and where it can help in the pharmaceutical industry in the drug delivery technology. So if we move into another use case, at this time to ceramics, why it is important to measure the surface properties is because ceramic powders compose or ceramic devices are composed of inorganic, non-metallic materials with partially crystalline structure, and from the powder, there's a material prep. Through the process, we get the actual device. So it is important to understand the properties at the beginning, so we know what production process so we can understand it. And so that's why it's clear that the surface of a ceramic powder determines the structure and the ceramic compound of the ceramic compound, and immediately influences the macroscopic properties. And so it means that it also affects the production process, which means sintering process, flowability, and other properties and functionalities. We collaborate on these samples with Karel Matza, and actually these studies were never done before, as it can be partially calculated from SEM signal, but it doesn't give us very much of precision. And otherwise, it's very hard to do differently. And so if we get into the sample, we can see over here an SEM image of zirconia powder particles. And they have very good mechanical properties, high strength and flexibility, heat insulators, etc. And that's why they are studied to be for use in telecommunication, environmental or dental products. And the key aspects of interest are: what is the surface roughness of the initial powder? And how does the ceramic powder surface is changed by the calcination process? So we have two types of powder which we measured. So this one is before calcination and after calcination. So in SEM, we don't see much of the difference. And the calcination process is a process of strong heating below its melting point. And so volatile components are evaporated. So if we have a closer look, we already see some differences. So raw powder looks like this, calcinated has some, looks a bit different. But what's more important is that the calcinated powder has easier moldability, higher flowability, and it's less compact. And we'd like to see if it is because the surface changed. And so if we follow the same procedure which I showed you before, we get the tip on top of the particle, measure the topography, and measure the roughness. We measure the same on calcinated zirconia powder, and we have some roughness. I like to show the comparison, so let's get to it directly. And already from the graph or from the cross section, we can see that there are changes because the basic roughnesses seemed similar, but what we found out is very different as a developed interfacial ratio. So it basically means that the macro roughness is the same, but the interfacial area is much larger. It has much larger surface per same distance. So that's this part, but where we see smaller peaks within the morphology. And that is the reason why macroscopical properties are different. So, or probably this reason. So it is less compact and it has higher flowability when calcinated. And so if I should summarize what we did in ceramics, or in the powder particles, we measure the surface roughness of both types of powder. And we had a look how the calcination calcination changed the surface, and we found out that the developed interfacial area was higher by almost 10%, which corresponds with the known higher flowability of the powder. And so this is a way how Lightscope can help in observing changes of the particle surfaces at the nanoscale, which are caused by various processes and can improve the fabrication technology, make it more reproducible, or change the fabrication technology of ceramic components if needed, so we understand the fundamental why the microscopic properties look different than the macro, or how it changes. And so to sum up a package for powders and particles, the workflow is quite transparent and effective. So it's very easy to find and select the specific particle. We can use the wide field in SEM. The measurement, then afterwards, as we approach, we can easily measure the particle surface either simultaneously or watching what is actually happening. And we can continuously have the control over the experiment. We included into our software some of the built-in functions, such as particle shape compensation, or various area selection boxes, or surface roughness calculation toolbox, and easy export of analyzed data into different type of files. And so this is a unique commercial solution for a direct measurement and calculation of the surface roughness of powders and particles within the NanoView software which we have. If we move into 2D materials, which are low-dimensional materials, usually laying on a substrate, quite flat substrate. So we can see over here graphene, and from the tilt, we see the very end of the tip. Even without tilt, we can see. And so that's quite easy to approach and to see where we actually are. What are two-dimensional materials? They are basically single-layered materials, either molybdenum disulfide, graphene, HBN, indium selenide. There are so many of them, and they are studied a lot due to their unique properties, and they are already used in automotive, semiconductor, petrochemistry, etc. And they play a crucial role in the development of new technologies, as nowadays everything needs to be faster, better quality. Two-dimensional materials are the one which can help us achieve that. And what is necessary in order to know how to reproducibly create such structures and use them in industry is to measure them complexly, microstructure defects, etc., and connect the material characteristics together to understand what is happening. So material behavior, fabrication processes, for quality control, for all of them, we need to know more about the 2D materials. What are the needs? Definitely repeatable localization and analysis of specific flake, because the flakes are usually quite small. It's necessary that we are sure that we are measuring the same flake. Then advanced characterization tools are required, so we can combine the data together and have more modalities. An ideal case is minimize the number of sample transfers. One of them to find the same local same flake, but as well to minimize the contamination. And then, of course, combine and correlate all the signals together so we are sure that it's from the same spot. And so let's get to the complex characterization. AFM-in-SEM, from the AFM part, we have 16 measurement modalities which can be used for measurement of precise topography, mechanical properties, electrical, magnetic, and chemical composition. And SEM has various modalities as well, and all of them can be used when they are in SEM. And all of them then can be combined, and we are sure that we are under in-situ vacuum conditions. So there should be no change in the sample. And so today I'd like to show you an optimized approach for a complex surface analysis. The case study I will show today is a molybdenum disulfide. It's yeah, I will talk about it later. And so what is the measurement workflow? First of all, we find the flake and we can do multiple measurements from AFM, SEM, EDS, EBSD, what we have. Then we need to merge the layers, and then we can correlate them. So all of it can be done now in the NanoView software. So if we have a look, and as well, it's now much easier. What we need to do is in 4 clicks, we will get the image. So now we are sweeping. It will automatically choose its own resonant frequency, and afterwards we just click approach. So that's why now the scale bar says that the scanner is going back and forth, up and down, and gets into the contact. And the last step was, I wasn't fast enough to say it, was the start button to start the actual image. So that's all you need to do. It's a 3-click measurement, and already you can see the data coming. Of course, afterwards can be improved if necessary, but otherwise this is the procedure how to measure. And how to merge layers. So we have a merge layer function where we choose what layers we'd like to add to the previous one. And as you can see, we just choose the layers, we can rename them and save it. And you get all the files, all the channels into one file, and you can work with it in one file. This is the case when you need to measure several times in row, so you don't have it in one image or in one single measurement, but as well, many things are possible to measure in single measurement. So this is the way how it can be done. Also, we included data correlation using CPAM+. It's a function based on machine learning. And so, first of all, we have trace and retrace. There are many times sometimes there are some artifacts. So we corrected it, and then we correlate the data using corrected topography in this case and secondary electrons image. And afterwards, we get the CPAM image, as you can see here. And it's all automated just using, here is automated function for AFM scan correction. And over here in the NanoView is AFM-SEM correlation. So you can choose if the mode should be rough or fine, and save the data. And so if we go into the use case, what we measured is the molybdenum disulfide. It's a flexible material with direct band gap. It has unique electrical and mechanical properties. Monolayer of molybdenum disulfide is suitable as a 2D semiconductor in advanced electronic devices. But the issue is the reliable and reproducible properties and fabrication. So that's why it is still studied, and we try to understand it. So we cooperate with Zdeněk who said that Lightscope simplifies complex characterization of his 2D materials and conveniently localizing specific areas within the SEM environment for comprehensive analysis, streamlining production, and quality control. So the samples look like this. We measured again 2 different types of samples. They are different in a way that they were prepared by CVD using CVD, but under different conditions. 300 nanometers silicon dioxide. And so what we wanted to see is whether the monolayer looks the same or different, or how the different condition changes the growth of molybdenum disulfide monolayers. And so we measured what is the height, what are the mechanical properties of such flakes, and what are the electrical properties. And afterwards, we wanted to observe the differences due to diverse fabrication conditions. So if we have a look at the first sample, we used SEM for localization. We can see high material contrast of flakes, but we can also see the bright spots are impurities. So it's definitely not completely clean. But we don't have the morphology information. When we measured the topography, we found you can see that there are much more impurities than we saw in SEM, as well the smaller ones. And we could measure the height profile and see that there are probably a second layer growing. And we found out with topography that the flakes are in sub-nanometer, which is of course correct as it's a monolayer. But we can also, it's not that much visible in this topography image because impurities were in 80 nanometers, something like that. Oh, 12 nanometers. And then we measured the electrostatic force microscopy, which measures the surface charge distributions. And we can see very clearly where the flake is and where it's not. And then we measured the phase imaging to obtain the mechanical properties. And afterwards, we took all the data and compared it with the So what we see in the phase imaging is that the flakes are harder than the substrate, and we can also detect. I wanted to talk about it later, but it's already visible that something is over here happening. So we measured the second sample as well and compared these data together. And so one thing I'd like to point out is that all the data were measured in a single measurement using one probe. So we are sure that the conditions were same. What we can see in the second sample is a brighter part in the middle of smaller flakes, which is probably the second layer. But everywhere else, we didn't see much except the phase imaging. And so have a look at the phase imaging. And what we can see that phase imaging detects the edges, and it revealed us some differences in the cost, probably due to growing process. So as we saw it in all the flakes. So we can see that in the second sample, we have the triangles over here, which we see in red, are centric. And probably the layers in this second sample are growing from the middle. On the other hand, the first sample, we can see the smaller and many of little triangles, which means that probably the second layer grows anywhere, and many of the beginnings of the second layer are over here. So this is something where we're not sure what we're gonna see in different channels. So it's good that we could measure it all at once and then compare what we see. And so if I sum it up, AFM-in-SEM with Lightscope offers us an optimized workflow for the multimodal analysis of 2D materials. We can see that there are different channels which we can obtain. So it enables us many techniques from both AFM and SEM instrumentation, and it helps us connecting different information about the same place. So if I sum it up as a package for 2D materials, we have an optimized workflow for repeatable localization of the region of interest, enabling us complex AFM and SEM analysis, which is time efficient. And it enables us a straightforward signal correlation and correction. So we can merge the layers from multiple measurements if needed. We can select the new area selection box and measure, zoom in, and we can use surface shape correction using 3-point fit or polygon or other fits. So it helps us easily obtain and correlate the various data and helps us in better understanding the complexity of material properties when one technique is not enough. I'd like to summarize my talk. So we talked about the AFM-in-SEM technology with Lightscope. What are the main benefits, which are in situ characterization, correlative multimodal analysis, and precise localization to the region of interest. And I introduced the optimized solutions for analysis of surface roughness of powders and particles in different use cases in pharmaceutics and in ceramic industry. And then we went through a multimodal analysis of 2D materials, where modes such as phase imaging, electrical properties, magnetic properties, EDS, or using fibbing and gissing can be helpful together. And so we presented these solutions. And so what was the main objective, except the use cases, which I'd like to point out, is that we actually use the SEM as a place where it's a controlled environment, and we can connect different signals from electron microscopy, such as secondary electrons, BSE, EBIC, EBAC, nanoindentation, using nanoprobing, nanomanipulations, AFM with several different modalities, all of them together, and we are sure that the environment is the same. We can control the temperature, etc. If you have any other question, maybe later, well, please reach us. We have quite a wide distribution network. We have local partners across the world, and we will be happy to answer all your questions. If you'd like to see more, you can visit our web. We regularly post on social media, so follow us, or we have a YouTube account where you can see it, or you can contact us directly whenever you like. Also, you can meet us at conferences. We will be in correlative material characterization in Brno, but as well in States, Japan next year, etc. So thank you for your attention, and we will be happy to answer all your questions. Thank you for watching. Bye.